It's basically a combinatorial problem. What we want to do is enumerate walks on lattices according to their algebraic area. So it's certainly an interesting problem per se, right? Enumerating things is always interesting per se. For me, as a physicist, I would say that this problem is also quite interesting because it can be mapped on the Hofstadter model. Maybe you have heard about the Hofstadter model, which is a very famous model in quantum mechanics. And as a physicist, I would say I am interested by this thing, of course, because it is relevant to condensed matter theory. The Hofstadter model deals with basically electrons in a plane coupled to a magnetic field. So this is very relevant experimentally. Experimentalists today can construct layers of electrons, and we can put a strong magnetic field. So we are in this situation of the Hofstadter model. Coming back to mathematics, the Hofstadter model is also quite interesting. It has fascinated generation of mathematicians, more precisely number theorists, because maybe you know that the Hofstadter spectrum is a rare example of a quantum fractal. So I will show you a fractal a little bit later, by the way. And another thing which was more unexpected to me is that this enumeration problem is also related to the notion of exclusion statistics. So what is exclusion statistics? It has again to do with quantum mechanics, with quantum statistics. You know that when you have n identical particles, the n-body wave functions in quantum mechanics can be either symmetric or antisymmetric. Symmetric, this is the bosons. Antisymmetric, the fermions. When you talk about exclusion statistics, you go beyond Fermi statistics. You have a stronger exclusion. It's a purely quantum concept. So I will explain this a little bit later. And what is nice with this mapping of this combinatorial problem of random walks on a square lattice that you want to enumerate accordingly to their algebraic area. So if you understand that you can map this on this Hofstadter model, that you have a relation to exclusion statistics, then you can generalize easily to other varieties of random walks on other type of lattices, right? So this is what I will try to explain during this. We are interested by random walks. So first on a square lattice, right? I will take the example of a square lattice to start with. This is a random walk. We start from its red point. We come back to the same red point after a certain number of steps. Obviously, for the walk to be closed, you need the same number of steps right and left, the same number up and down. So the total number of steps is an even number for the walk to be closed. So what is the algebraic area of this particular example? What is the algebraic area? It is defined in terms of a M winding sector. And what is the M winding sector? It is the lattice cells inside the walk, which has been enclosed M times by the walk. So you see, the walk can do that M times, or it can do this M times, right? So in one case, M will be positive, and in the other case, M will be negative. It's really an algebraic area. It can be positive or negative. It is not the arithmetic area inside the walk. It is something more sophisticated. It is the algebraic area, which can be positive or negative. And how do we define the algebraic area? In terms of this M winding sector. So we define Sm. This is the area of a given M winding sector inside the walk, which is the number. M is in fact the number of lattice cells inside the walk, which has been encircled M times by the walk. And the algebraic area is simply the sum of these Sm weighted by M, the sum of M Sm. So let's return to the walk I showed you 2 minutes ago, and let's compute its algebraic area. So it's again the same walk I showed you before, but now I simply put the winding sectors inside the walk in different colors so that you can see them easily. So let's look at this lattice cell here. It has been encircled once by the walk in the negative direction. So it's winding sector -1. Also there you have the winding sector -1. Here, these two cells are +2 winding. Why? You see that the walk went twice around these two lattices. First here, and then second inside the walk itself. So it's a +2 winding sector. Here it's a 0 winding sector. Why? The walk went once in the positive direction and once in the negative direction. So +1, -1, 0. And then this yellow lattice cells have winding +1. So these are the winding sectors for this work. And if I compute the algebraic area, I will obtain, again, 2 lattice cell winding -1. This is the 0 winding sector, it doesn't contribute. 14 cell winding +1, 2 cell winding +2, I get 16 in this example. So this is the algebraic area. So the question we ask is the following. You consider all possible work that you can draw, starting from a point, coming back to the same point after n steps. By the way, there is n over 2 square, n choose n over 2 square such walks. This is the number of all possible walks, making n step closed. Each of them enclose a certain algebraic area. The question we ask again is what is the number, Cn of A, of walks with algebraic area A? Okay, so this is the enumeration problem that we want to answer. So you have obvious thing. Of course, the total number, if you sum Cn of A of all possible A, you will get the total number of walks. It's obvious, right? An obvious thing also is that since you have equal probability to do this or to do that, Cn of A and Cn of minus A are equal. So these are obvious things. But of course, what is Cn of A? So a less obvious step, first step that we can do is to introduce 2 lattice hopping operators on the lattice. So U goes right and V goes up. And we decide that U and V do not commute. So here we are, non-commutative geometry. VU equal QUV. So it's a very simple manifestation of non-commutative geometry. Select in U plus U minus 1 plus V minus 1 power n. N is the number of steps, an even number. You select the part which is independent of U minus 1 and V minus 1. If you think to it a minute, this is obviously Cn of A, right? It gives you obviously Cn of A. So this thing here, power n, is equal to what we are looking for, plus extra term, which will include U minus 1, V minus 1, etc., etc. So Cn of A is here. For example, take walks of length 4. It's a back of an envelope computation to convince yourself that this thing will be 28 plus 4q minus 1 plus. What does it tell you? It tells you that among the 36 closed walks making 4 steps.
Excuse me, a question. Are these operators like formal, or they act in a very specific way on the lattice? Like we declare they do not commute, but do they
I declare that they do not commute.
We declare it, so we just.
I declare it. Yes. What is your question?
How do they actually act on the lattice?
I will show you later.
Thank
I
you
will
so
give an example of this later.
Good. Okay, thank you.
So for the time being, it's just a non-trivial commutation between U and V, which simply tells you that if you do this and this, or this and this, it's not the same thing. There is a Q in the middle, right? A factor of Q. Among the 36 possible closed walks making 4 steps, what you can compute by this and check that indeed 28 enclose an algebraic area 0. For example, this one, 4 steps, algebraic area 0. 4 will enclose an algebraic area +1, this one, 4 steps, and this is algebraic area +1, and 4 algebraic area -1. So this is the first thing that we can say. Now, a second thing that we can say, which is even less obvious, that if you rewrite this non-commutative parameter capital Q as exponential 2i pi phi over phi 0, where phi is the flux of a magnetic field perpendicular to the 2-dimensional lattice, and phi 0 is the flux quantum. So it comes from quantum mechanics. It has a dimension of the flux. It's a flux quantum. So phi over phi 0 is dimensionless. So if I rewrite Q like this, then the algebraic area enumeration is mapped on the quantum mechanics of a particle hopping on the square lattice in a perpendicular magnetic field. This is the Hofstadter model. So the Hamiltonian of the Hofstadter model in this language.
I'm just a little puzzled there. You say trace, so we want an operator there. We've got H, E, and what's the operator operating on and how? You're taking trace of something.
Okay, I will come to the trace in a minute. Just let me come to it. So the Hamiltonian will be U plus U minus 1 plus V minus 1. In quantum mechanics, U and V are translation operator on the lattice. They are precisely defined. They commute with this Q, which is exponential 2i pi phi over phi 0. And maybe this is your question, I don't know, but to come back to this thing here, selecting the part here in this power n, which does not depend on u, u minus 1, v, or v minus 1, in quantum mechanics, amounts to compute the trace. So I take this operator, h over n, and I have to compute its trace. So I will define this maybe more precisely in a few minutes, if you are not happy with my answer. But formally, you have to compute the trace of this operator, which is a quantum operator, right? So, for the time being, U and V are infinite dimensional matrix. I will define this more precisely in a minute. Okay, so we see that we map this enumeration problem for classical work on the square lattice to a quantum problem, which is the Hofstadter model, with this Hamiltonian and this trace, which gives directly what we are looking for. So the question is how to compute this trace now in quantum mechanics. So lattice work combinatorics is the Hofstadter quantum trace. How to compute the trace? Maybe this was your question. We have to simplify a little bit. A simplification in the Hofstadter model appears if the flux phi divided by phi 0, the quantum of flux, is a rational number, where P and Q are two co-prime integers. So this capital Q now is exponential 2i pi P over Q. So now we have a Q time Q matrix representation. So this was maybe your question, I'm not sure, but of U and V. So this lattice operator, translation lattice operator in the X and Y direction, are now realized by Q matrices. And this is the quantum torus algebra.
This U and V, the matrices here, are exactly the same as the actions of the S and T in the Heisenberg group in the last talk on this space.
Yeah, of course. This is quantum torus algebra. It's a well-known algebra, indeed. And what we have here, we have two quantum numbers, kx and ky. There's like pseudo momenta. We are in 2 dimensions. We are in quantum mechanics, one particle, 2 dimensions. We need 2 quantum numbers. These are the 2 quantum numbers, kx and ky. Okay, and so the Hofstadter matrix, the Hofstadter Hamiltonian, which is u plus u minus 1 plus v plus v minus 1, becomes a q by q matrix. Okay, so now we can define the trace. How do we define the trace of this q by q matrix? We have to compute the eigenvalues of this q by q matrix. We have q eigenvalues, E1, E2, blah, 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 EQ. Power n, take the sum, and we have to integrate all of these 2 quantum numbers, kx and ky. This is, of course, difficult to compute. Defined like this, it's very difficult to compute this trace. Now, to make just a small parenthesis and to come back to this Hofstadter model, Hofstadter spectrum, which is a fractal, we can plot E1, E2, EQ. They are functions of kx, ky. We can vary kx and ky between 0 and 2 pi and plot the spectrum. And if we do that, we obtain the Hofstadter butterfly. So this is a fractal I was mentioning. So what do we have here? On the horizontal axis, we have P over Q, which can always be taken between 0 and 1 by periodicity. And on the vertical axis, we have the possible energies, E1, E2, E3, EQ, as function of kx and ky, and both kx and ky vary between 0 and 2 pi. And you get this picture, which is a fractal. Okay? And this is known under the name of Hofstadter butterfly, because it looks like a beautiful butterfly, as you can see. So to come back to my problem, how to compute this trace? So this is the trick to compute the trace. You can deform the square lattice. You are going to do a modular transformation, replacing u by minus uv and v remaining the same. This amounts to deform the lattice. The square lattice becomes now a banded lattice. But the enumeration problem is exactly the same, right? There is no difference. Simply the lattice is slightly... So if we do that, if we use this new Hamiltonian, which is equivalent to the previous one, but now for this banded lattice, h equals minus uv minus v minus 1 u minus 1 plus v minus 1, we get this q by q of Hofstadter matrix, which has now a simple form. Why it is simple? You see that the main diagonal is 0. You have 2 subdiagonals, I think you say that, subdiagonals, here and here, which depends on this function, omega of k. So you have omega and omega bar. And basically, that's it, right? We can even ignore omega q and omega bar of q on the corners. If you forget about these two corners, you have a very simple matrix with a main diagonal, which is 0, surrounded by two subdiagonals, omega and omega bar. And this omega, again, is defined in terms of kx, ky, and this capital Q being exponential 2i pi p over q, right? From this matrix, you can compute the secular determinant, z of 1 minus zh, and you get this result. So you see that the kx and ky part, this momentum, quantum momenta, is on this side. And on the other side, you have something which does not depend on kx and ky. It's a polynomial in power of z, this parameter z here, with coefficient z of n. You can compute the z of n. This z of n rewrite as trigonometric multiple sums, which are given here. This is z of n. This has been obtained by Kreft in the 90s. Sk, this function here, skn, skn minus 1, etc. This function is given by 1 minus qk times 1 minus q minus k, which is simply 4 sine square pi k, again, p over q. This is an interesting result. And now if you look at it a little bit more seriously, you say, look, what is this? If now I interpret sk, this function, which appears here, as exponential minus beta epsilon k, where beta is the inverse temperature. So now we are in statistical mechanics. Beta is the inverse temperature, and epsilon k is a one-body spectrum. So what we say is that we have n particles. N here is the number of particles which are going to populate one-body quantum state of energy epsilon 1, epsilon 2, epsilon 3, etc. So this sk is really now a spectral function. So if you take this point of view, this interpretation, then this z of n is the n-body partition function for particles with one-body spectrum epsilon k and obeying g equal to exclusion statistics. So what I mean by g equal to exclusion statistics? Let me give you an example of this z of n equal 3. So this is three-body problem, z of 3. Let's set q equals 7. So I write z of 3 for q equals 7. I get this. You see that in this sum, you will never see S1, S2, for example. You will see S1, S3, S3, F7, whatever, but you will never see product of two consecutive quantum numbers. There is neither 1, 2, 2, 3, 3, 4, 4, 5, etc. So it means z of 3, you can rewrite it that sk1, sk2, sk3, where k2 is bigger than k3 plus 2, and k1 is bigger than k2 plus 2. There is this exclusion plus 2, right, between one-body quantum state, which are occupied by these three particles. So this is G equal to exclusion, right? It goes beyond Fermi exclusion, because Fermi exclusion, you will have S1, S2, S3 in this. Fermi exclusion, you can populate neighbor energy levels which are next the one to the other. In the case of G equal to exclusion, you have to leave an empty quantum state between two occupied states. So you go beyond Fermi exclusion. This is called G equal to exclusion in that case. Okay, I could explain a little bit more where it comes from. It is in fact related to the Enian model. The Enian model being the quantum mechanical realization of the Bragg group. Okay, so some people mentioned the Bragg group during this week. This Enian statistics is the quantum realization of the Bragg group in quantum mechanics, and exclusion statistics is a particular continuation of this Enian statistics. Okay, anyway, the only thing which matters is that we go beyond Fermi exclusion. We have particles which are more excluding themselves than usual Fermi. Okay, so now we are in statistical mechanics. We have an n-body partition function, z of n. We can compute the cluster coefficient, b of n, which are associated to z of n. So we simply take the log of the sum of z of n times z over n. And from this, we can deduce the bn, which this bn are called the cluster coefficients. Okay? In statistical mechanics, you have the partition function, and then you have the cluster coefficient defined in this way. And if you start from this z of n, you can compute the b of n, and they are given by this formula. So here we have three parts. We have now a single sum. Here it's a multiple trigonometric sum. Here it's a single sum now in terms of this S, the spectral function. You have this coefficient here in blue, and you have a sum here over L1, L2, Lj, composition of n. So what do I mean by composition? The composition of n means the ordered partitions of n. Of course, you know that, but for those who do not know, I just remind you that in the case n equals 4, for example, you have 4, 3, 1, 2, 2, 2, 1, 1, 1, 1, 1, 1. These are the usual partitions. And then you have to consider additionally for the composition 1, 3, 1, 2, 1, 1, 1, 2. So the composition are the ordered partition of n. So in this formula, again, we sum over, this is b of n, we have to sum over all possible composition of n. Now, the coefficient C2 here is this product of binomials in terms of the L's, L1, L2, L2, L3, etc. And as I told you, the last part is a single sum now, which can also be computed. Okay, so we know Bn. We know what is the Bn. We know the cluster coefficient, B of n, which is associated to this n-body partition function with exclusion 2, defined in this way. So now you are going to tell me why B of n? Why computing B of n? If you lose the fact that the log of the det of 1 minus zh is the trace of log of 1 minus zh, and if you work a little bit, so we have to get rid of kx and ky. I have no time to explain to you how it works, but you can do that. Believe me, at the end of the day, you realize that the trace that you are looking for is in fact B of n, right? So remember, this n is an even number because we have an even number of steps to have a closed work on a square lattice. N is, so n boldface even is 2n, it's even. And this is this n which appears here in B of n. So we have the trace of h power n. We know what is the trace of h power n in terms of this B of n. And since, as we know, the algebraic counting is given by this, the algebraic area counting is given by this formula, we have Cn of A. Okay? So let me give you Cn of A. This is the answer to this enumeration problem of closed random walk on a square lattice, making n steps enclosing a given algebraic area A is given by this formula. And we could check, for example, by taking again 4, n equals 4, but this formula will give you back the 28 and the 4 that we discussed at the beginning for this for these walks on length 4, right? In the case n equals 4, you have only two compositions, the two compositions of 2, 2, 0, and 1, 1. You can work out this formula and you will recover what we obtained before. Okay? Good. So, how much time do we have? So now you could tell me very well, but what next? Well, if now we think again in terms of this exclusion statistics and this Hofstadter matrix, I remind you that the Hofstadter matrix, I'm going to show it again to you, given by this. This Hofstadter matrix is given like this. You have a 0 on the diagonal and 2 diagonals on each side, omega, omega bar. If you think in terms of this matrix now, you realize that in terms of G equal to exclusion, what you are dealing with in general is this kind of matrix. So again, a vanishing diagonal, a function f on one side, g on the other side. And if I compute the determinant again of 1 minus zh, the secular determinant, I will generate this z of n, I showed you before, for a spectral function g of k times f of k. This is what we have to consider now. So now we can move to G equal 3 exclusion. So G equal 3 will be again the same type of matrix, but now you have two diagonals made of zeros. And again, on both sides, f and g, and basically 0 everywhere else. And if I would compute the det of 1 minus z h3, I will obtain an n-body partition function for exclusion 3 with spectral function given by g of k times f of k times f of k plus 1. Okay, so I can continue like that. And finally, define a general Hamiltonian for G exclusion. The Hamiltonian will be for G exclusion, f of u times v plus v 1 minus g times g of u, where f and g are functions of u minus 1. This is a general G exclusion Hamiltonian. Look, if we come back to the Hofstadter case, it was G equal to, you remember? Remember this Hamiltonian, minus uv minus v minus 1 u minus 1 plus v minus 1. This is indeed 1 minus u times v plus v 1 minus 2, 1 minus u minus 1. This is indeed G equal to. Okay? So this is the general form now of this G exclusion matrix, of this G exclusion Hamiltonian. It's not necessarily Hermitian. It's a good question, and I will show you an example where it is indeed non-Hermitian, and it's described chiral walks which has an orientation. But it doesn't have to be Hermitian. Not necessarily.
Okay.
You have zillion of models where the Hamiltonian is not Hermitian. Exclusion models. And, indeed, it's not necessarily Hermitian. You're right. Spectrum is real if there is CP or PT or CP invariance, I don't remember.
And yours, the spectrum is real?
I don't know, but I don't care. It's not my problem.
So
No, but to be frank, it's not my problem. I want to enumerate closed random walks. This is my problem, right? So if the Hamiltonian is non-Hermitian for sure, does it have a real spectrum? I don't know. In fact, I never asked myself the question, but it's a good question. I should maybe try to. Now I have this G Hamiltonian, I have this G exclusion matrix. Again, the same thing, right? I have now G zeros here in between these two blue diagonals. Okay? And if I would compute now the determinant of 1 minus z hg, I will obtain a z of n for G exclusion with spectral function g of k, f of k, fk plus 1, up to fk plus g minus 2. Okay, so let me give you quickly this, indeed, z of n in that case. This is the z of n for G exclusion, the n-body partition function for G exclusion. So I have a shift of G now here instead of 2. This is G, not 2. And I can again compute the cluster coefficient. And I will obtain a formula which is quite similar to the one that we have obtained before for G equal to. It's basically the same formula, but the only difference is that now I have to sum over the G composition of n instead of the usual composition of n. And this blue factor here depends on G. Okay, but it's the same formula, basically. Okay? So what are the G composition? G composition, you can insert at most G minus 2 zeros in succession, inside the usual composition. Look at 3. 3 is 2 plus 1, 1 plus 2, 1 plus 1 plus 1. If I have G equal 3, I can insert 1 0 where I want inside the composition. So I will get 2, also this one, 2 plus 0 plus 1, 1 plus 0 plus 2, etc., etc. And for the 4 composition, G equal 4, now I can insert 2 zeros, no more than 2 zeros in succession. So for example, I will have for 3 again, 1 plus 1 plus 1 is 3, but I will have 0, 0, 0, 0 here. Okay? So these are the G composition, the generalization of the usual composition. And this coefficient in blue here is also known. This is a spectral, again, a single trigonometric sum, which can be computed. So we can do everything again. We know CG. Let me give you CG. CG is given by this. So this is the generalization of this product of binomial I gave you before for G equal to. And now we have to consider random walk on a lattice of length n, which is now Gn. Remember before, for square lattice walk, n was even. So ball face n was 2n, and now ball face n is Gn. Okay, so simply to tell you that the algebraic enumeration, if there is a random walk which corresponds to this Hamiltonian, then its algebraic array enumeration is going to be given by this formula. I know what is CG, I know what are the G composition, and I know what is the spectral function S. So I know everything again. Okay, so now to answer your question, but to show you an example in answering your question, let's focus as I have still 1 minute or 2 minutes. Good. So let me give you an example for triangular lattice Carroll walks. So these are Carroll walks. So this is why the Hamiltonian is non-Hermitian indeed. For G equal 3. So we have a triangular lattice now. We have 3 hopping operators, U, W, and V. That's all. So you see that we can either do this or we can do that. These are Carroll walks now. They are not, it's not U, U minus 1, V, V minus 1, right? These are Carroll walks, and the Hamiltonian is indeed non-Hermitian. So what is the Hamiltonian? It's U plus V plus W. Now, again, I do a redefinition of these 3 generators, U hopping operator, U, V, and W, in terms of my usual small u and small v. Capital U is minus I UV, capital V is I U minus 1V, and I get now this Hamiltonian. And you see that this is a G equal 3 Hamiltonian. If you go back to the general definition, you remember we had 1 minus G, here it's 1 minus 3, V minus 2. So this is a G equal 3 Hamiltonian, okay? And the spectral function, which is given by G of K times F of K times F of K plus 1, in this case becomes this trigonometric function. Okay, so I can compute everything. I have the algebraic array enumeration. I don't give you a formula, but it's there. You simply have to use this formula here for G equal 3, S given by this function I gave you 1 minute ago, and you have the algebraic array enumeration for this Carroll walks on the triangular lattice with indeed a non-Hermitian Hamiltonian. Okay, so I think maybe it's time for me to stop. Thank you.
I have some comments. So, because here there are different people working on something which I think maybe they notice something connected with this work. So, can you show the slide where there is the H, which is written in terms of U plus U minus 1 plus V plus V minus 1? Is at the beginning?
You want this matrix?
Yeah,
or?
the one. Okay, the one at the very beginning, just U, U minus 1, V, V minus 1. Yeah, okay. So actually, this H, okay, if you take U plus U minus 1, so they satisfy the quantum torus. This combination U plus U minus 1, let me call it A. And V plus V minus 1, let me call it A star. Actually, A and A star, they close on some relations that are called the Askew-Wilson relations. In this case, you are considering the Askew-Wilson relations when Q is a root of unity.
Yes.
So the spectrum that you are considering for H, this H, recently is a special case of what is called the Owen Askew-Wilson operator. And some people here are working on that. So maybe they noticed this connection, I don't know. But, okay, so is that for the diagonalization of this Owen Askew-Wilson operator, one tool is to use the representation theory of the Askew-Wilson algebra. So in that case, the representation theory of for this Askew-Wilson algebra at the root of unity has not been done. For Q generic, it's called the theory of Leonard pairs. Mm-hmm. So maybe I don't know if Walter Williger is listening, but maybe it will. Maybe for him, it will give some motivation to look at this Q root of unity.
So it has not been done in the case rational.
It has not been studied. So I just sent him some email to check, but I think it has not been studied for the cyclic representation of. Okay. So another point. So when you go from this H to the other H, so from this perspective, okay, of Askew-Wilson algebra, so U plus U minus 1, and A star is V plus V minus 1, and you go, so now you can show the other.
So you make this transformation,
okay.
And then you get the new H, which is here.
Exactly. Okay. Now you have a new A star. Okay. And this can be seen because from the point of view of Askew-Wilson algebra, for those who are working on this stuff, this is another type of Euler-Wilson operator. So I just checked that indeed, when you consider, for instance, A and A star, the initial one, and you calculate the Q commutators of A star, you produce the first guy, the UV plus V minus 1, U minus 1, and whereas the second one remains. So it's like you go from, so Exclusion algebra has different types of presentation, is in terms of 3 generators. So it's like you are considering initially the H for the A and A star, and then you go to another H where you have the Q commutator of A star and A star. And you are
Okay, yeah, sure.
So that's
Okay.
Does the Z of n satisfy some reference relation?
C, the what?
Z of n?
Z of n?
Yeah, the big Z of n.
Yeah, so in fact, the Z of n have been obtained by Kreft by solving a recurrence relation. You're right, yes.
What is it? Do you mind telling me?
I don't have it right now in my brain, but I can show it to you if you want. This Z, effectively, this thing is our solution of recurrence relation. Indeed. This is the way you compute this Z of n. Indeed.
Do you want
Yes?
to see what kind of
Carl work with the
Yeah,
denomination
Carl,
and everything.
Algebra 2 was
Square lattice work.
Okay, for general G, what's the answer? Polygons?
I don't know. It's a good question. To be frank, we have for other example, it becomes a bit obvious. But indeed, you're right. It would be nice to try to classify all possible works on various lattices accordingly to this kind of classification. So so hexagon, good question. In fact, I had a slide on the hexagon. Then here, in that case, the statistic is more complicated. It's a mixture of fermions, which are G equal 1 and G equal 2 particles. So it's what I meant. It becomes a bit, of course, for physics, it's very nice, but it becomes a bit complicated, not very simple and obvious. So here, in that case, for hexagon work, it's on a lattice, it's 1, 2 statistics, a mixture of 1 and 2, G equal 1 and G equal 2.
Again, then?
Okay, thank you.